So I think we can start. So over the last two lectures, we were discussing about latent variable models, right? And within latent variable models, we were particularly focusing on variational autoencoders or VAEs. So the idea for today is to wrap up our discussion on VAE so that in the next lecture we can start with flow-based models or GAN. I'll select which one to start, but one of the two. Either flow-based model or GAN we will start in the next lecture, which is on Friday. But today we will wrap up our discussion on latent variable models or VAE. Now, because we are going to wrap up things on VAE, let us first recap all the things that we have discussed in the last two lectures. So if you remember, this is where we started, right? That we assume that if there is a data set X, there is some hidden factor, hidden features that is the reason for the data, and that is Z, and you assume Z to be coming from some easy to sample distribution, which is Gaussian, but can be other things also. And then X given Z, because it is conditioned on that feature, it is simpler, and so that is also from a simple distribution, which is a Gaussian, where your mean and covariance is parameterized by neural network, and so those neural network parameters are theta. Those are the weights and biases of your neural network. Z is your, and those are also function of Z because it is conditioned on Z, and Z is your hidden variable, latent variable, right? And so with that, this basically is a two-line equation that describes any latent variable model. I mean, this is not specific to VAE. This is specific to any latent variable model. Yes, the neural network will not be there, let's say, for a mixture of Gaussian. And the distribution can change. Gaussian can become categorical for mixture of Gaussian, and so on and so forth. But these two equations, if I generalize it as P and Q or P and P, then that is basically what a latent variable model is, right? But in VAE, this is the setup. Z is Gaussian, X given Z is Gaussian, but X given Z, the parameters are modeled as neural network with parameter theta. Okay. How do you train such a model? Well, for any model, our obvious solution or obvious choice is to train it using maximum likelihood estimation. So we will like to compute the likelihood, which is in the last equation. If you focus on it, the last equation, you will see the likelihood is there here, right? And that likelihood you can decompose because of the IID assumptions. So each data is a IID, so it becomes a product. You do not really work with the likelihood, you work with the log likelihood. So you take a log and you end up with this term, the last term, which is log of Px given theta. But this you cannot work with because Z is not observed. So you have to integrate out Z, which is kind of intractable, high dimensional, right? So you cannot really work with that. So what you do is that you come up with the idea of the, is it somewhere here? I don't see it here, but you come up with the idea of elbow, right? So because you cannot compute it analytically, MCS is an option. MCS is very slow. So you don't use MCS. You go to importance sampling, and in importance sampling, you come up with the idea of elbow, right? Which is somewhere here. So this is the elbow, right? And we saw that how we come up with the idea of elbow. Elbow is much easier to work with, and so in latent variable model we work with elbow. So elbow is our loss function or negative of loss function because you maximize it, loss you minimize. So negative of elbow is your loss function. Let's put it that way, right? And then we said that okay, but for elbow there is a QZ that is sitting here, and QZ comes from the importance sampling concept. So what is the best QZ we can have? And then we did some derivation and we ended up with the fact that the best QZ is probability of Z given X. But that probability of Z given X is again intractable, and so we said, and that is dependent on X. So we said we will parameterize, we will bring in the concept of variational inference. There will be variational distribution parameterized by variational parameters, which were your phi, right? Which was your phi. Uh, yes, the phi you see in the second line, second bullet point. Those were your phi. So your variational distribution is probability of is something that wants to approximate probability of z given x. Now this variational distribution is function of x or data point, which means for each value of x, each data point, you will have a different q, and hence you will have a different phi. So if you have n data point, you will have n, or m data point if you will have m parameters, m phase, right? And so then your training will means that you want to learn theta, but you also want to learn this m phase, and this phase are vector. And then this is the algorithm where we ended our last lecture. So our last lecture ended with this algorithm, that with this setup, how can we train this model? And training was kind of straightforward. You will first initialize your parameters as always. Then you will select one data point at a time. With that data point for free, you will get one parameter vector, one vector, which is the parameter phi. So if you select xi, you get phi I. For that phi I, you update it until some level of convergence. We call it phi I star. And then for that phi I star, you then update your theta. And this whole nested loop kind of continues for certain number of iteration or epoch, whatever you want to call it. So this is where we ended the last lecture. So the last lecture ended with this algorithm. And I told you that for using this algorithm in practice, there are certain challenges. The first challenge is, how do you compute the gradients? Because you need to compute two gradients here. One is L with respect to phi, that is in what, bullet point number 3, and the other one is L with respect to theta. Theta is basically your generative model parameters, phi is your variational parameter. So we need gradient with respect to both of this, right? So with that, I hope you remember now what we did over the last two lectures. So let us start by trying to see how we can compute the gradient, if it is easy, if it is difficult. So let us see that, and from there we'll go to the other challenges and try to address those. And in the process, we will wrap up, or we will converge to the VAE that most of you probably already know. We will converge to the VAE that most of you have seen, right? I mean, what you are seeing for last two lectures is nothing like the VAE you have seen. So we will converge to that by today or today, and yeah, and that will be the end of VAE kind of, right? Okay, so now with that, let us start with, we want to compute the gradients. Okay, and there are two gradients that we want to compute. Let's start with the second one. The second one was with respect to theta. Okay, so let's start with the second one. So we want to compute, let's say, gradient with respect to theta of L, which is function of x. Xi I can write. I'm not writing I, but assume it to be one data point. It can be many also, but comma, it is function, or semicolon rather, is function of theta and phi. Again, to generalize it, I have removed the dependence on I mean, but that doesn't matter really, right? So this is what we want to compute. Remind me, what is the form of this L? Can you remind me how this L looks like? Expectation of log of P of, I'm writing it, but let's see. It is Q P Z log of P x comma z given theta divided by Q, P, Z, dz. This is the L, the elbow, right? And this elbow is nothing but expectation. We know that it is expectation of this with respect to that Q, right? So let us write that. So this is equal to gradient with respect to theta, and then expectation with respect to Z sample from Q phi, and then log. I can write as subtract, but I'm not writing that. So I just write it like this: x comma z given theta, and then Q phi of z, right? This is the expectation. Integration of fx gx dx is expectation of gx with respect to fx, right? And now because it is expectation, law of large number comes into picture. We ultimately we want to do it using sampling, and that's why important sampling came into picture in the first place. So with law of large number in the picture, we'll write this as summation. So let us write it as summation. So this is approximately equal to gradient theta, and let's assume I have, I don't know how many k number of samples I draw from here. 1 by k summation over j log of p x comma z j theta by q phi of z j j, okay, where zj is a sample drawn from q of z, and q of z is parameterized by p. Keep that in mind, it will be useful in a short while, not now. So q phi of z, this is sample from q phi of z, right? Because that is the distribution which with respect to which the expectation was expressed. So whatever distribution, the expectation is always with respect to some distribution. So that means you draw sample from that distribution, and then you do this, right? So that is why z comes from q of phi, obviously, right? So now, if this is the case, what is gradient of summation? Summation of the gradient. The gradient can go directly inside the summation in this case. Okay. So this is equal to 1 by k summation over j gradient with respect to theta log p x comma z j theta. I did some step jump, which should be obvious. What did they do? Minus term is not a function of theta, so it will become 0. So that term I have not written. I mean, log of a by b is equal to log a minus log b. Log b is not a function of phi, so theta, so that will basically go out of the window. Okay, simple. And that's how we can compute the gradient. Very straightforward. Computing gradient with respect to theta is trivial. It is nothing, right? You just compute gradient of each of those with respect to you compute gradient of each of the samples basically with respect to your. Good question. Yes, I said that, and that is why we went to the importance sampling. Importance sampling is also based on law of large number, right? So this is the importance sampling actually, because there is Q sitting there, and I'm sampling from Q, not from P. So it is actually importance sampling, but importance sampling is also an application of law of large number, right? When I'm saying Monte Carlo is a broad terminology. Any sampling based method is actually Monte Carlo, be it metropolis testing or whatever, right? So in that sense, okay. So the fact that Z is coming from Q itself says that it is actually important sampling that I am doing, right? Clear? Simple. Let's go to the non-trivial one, right? There is one more derivative or one more gradient that I want to calculate, which is the with respect to P. So let's go to that one. So next one is I want to compute gradient with respect to phi of x theta phi, which is equal to, we'll write the same exact thing, gradient with respect to phi. I'm not writing the integral form any longer, I'm just writing the expectation form, right? So it is expectation z from q of phi log p x comma z given theta divided by q of p z. Okay, one thing I will mention here, not that difficult, but because I am using two different notations simultaneously, let me say. So q of phi, q phi of z actually means q of z given phi. Similarly, p of x comma z given theta means p theta of x comma z. I mean, these are same notations written in two different forms. I am intentionally writing both the forms so that you are habituated with both. So whatever is the parameter that can either go in the subscript or as a conditioning variable. So p of x comma z given theta means p theta x comma z. And similarly, q of phi z means q of z given phi. Okay. So they are basically the same notation, or just different ways of writing it. Okay, so maybe you take a note of that so that you don't confuse these two notations, right? Okay, so this is the thing. Now, again, the expectation I can write in terms of summation, but this time the gradient I cannot put it inside. The gradient cannot go inside the summation. Any reason why? Because that has nothing to do actually. Okay, you were saying something? Correct. Sample, whatever sample you are getting is function of phi. So if when you are sampling it, those samples itself are function of phi. Phi changes, your samples distribution changes. And if that changes, so everything changes. So because of this complex dependency, you cannot use it directly. Because your sample z is coming from q phi of z. So if phi changes, the mean shifts, the standard deviation shifts. And so it's not that, so you cannot go inside. Because you have to keep in mind that all the z's that you are getting is actually from some distribution, and that distribution is parameterized by the phi with respect to which you are trying to take the derivative. In the previous case, I could do that because z was coming from the distribution q phi of z, but the gradient I was taking with respect to theta. Theta was not interfering with the distribution from which I was sampling. In other words, the sampling distribution was itself not changing. So the samples were always from the same distribution. And that is why when it was with respect to theta, I put theta inside the summation. But now the samples are functions of phi. And so you cannot do that. So you will need to find some alternative tricks for that. Okay. So in this case, case, as the expectation is with respect to z coming from q phi, we cannot push gradient of phi inside the expectation. So this is what I told just now, just some maybe a little bit scientific way of writing it. Okay. So because the expectation is with respect to phi, so gradient of phi cannot be, I mean, it is not that expectation of gradient of phi and then expectation with respect to phi, it cannot be reversed or swapped directly. So what to do? So there are strategies that allows us to compute such gradients. The most popular one is perhaps reinforce, which is used in reinforcement learning, but we will not use that. You don't need that for VAE. Later, if we need it sometime, we'll come back, but we'll see about that. So reinforce is one technique that allows you to do this kind of gradient independent of the form of Q of phi. And for any Q of phi, as long as you know Q of phi and you can sample from Q of phi, you will be able to do this thing for using reinforce, right? But in this case, we will not use reinforce, we will use a much simpler trick, which is known as reparameterization. So we will use the reparameterization trick to compute the gradient. Now this reparameterization trick is actually very simple, but it is not universally applicable. It is, first of all, it is only applicable if Q of phi is continuous. If Q of phi is discrete, PMA reparameterization scheme is not applicable. On top of that, there is some additional constraint which I'll talk about in a short while. Okay. So we use the reparameterization trick to compute this gradient. Okay. So that is basically the method which I'm trying to give. So we use reparameterization trick. Okay. So what is this reparameterization trick? Let us look into that. And for looking into this reparameterization trick, I do not want to write this long expression again and again, which is log of P and Q. So I don't want to write that. Let us compress it and write one, because that's a function, right? So let us take any function. So reparameterization trick. Okay. So suppose, to understand this, so suppose let us, we want to evaluate gradient with respect to phi of an expectation, let's call it, where the expectation is coming with respect to, let's say, z from Q of phi, and then there is a function inside, and that function can be a generalized function, let's call it b of z. We want to compute this gradient. So you can see that it is the exact same setup as the one we need. The only change I have done is that instead of writing that log p by q, I have written that b. You can easily imagine that b of z is nothing but log p of x comma z divided by q phi of z. That's what this b of z is. I just don't want to write that again and again, so take a short terms. This is generalized. Okay. Now, as I said, reparameterization trick is not applicable for any distribution. It is only applicable for certain distribution, and definitely that distribution has to be continuous. So we additionally assume that, let's say, Q of phi is Gaussian, because it is applicable for Gaussian. Okay. So we also assume that where Q of phi is basically a Gaussian with mu comma sigma square. Okay, any univariate case I am taking, you can take it make it multivariate. The trick will not change. Yeah, some product might become matrix vector multiplication, but nothing else will change. So with this setup, what is my phi? What is my phi? Mu and sigma square. Those are the parameters of my variational distribution. So my variational distribution is Gaussian, and the parameters are mu and sigma square. Okay. Or mu and sigma, right? I don't need to write square here. So mu and sigma. Okay. So with this setup, now we want to compute that gradient. Okay. So we want to compute that gradient with this setup. Now, if I use the law of large number, I mean write it in terms of samples, I can write it in two ways and check and see if you agree with that or not. The first way is what we have been doing. So grad of phi expectation z with respect to q phi, this is equal to, and I can write it in two ways. The first way is I will sample z from q of phi and then use those z's to write it as a summation, right? I will sample z from q of phi and then use those samples to write this expectation as a summation. If I do that, this will look something like, make it approximate. So 1 by k summation over j, and there is b, so b of z j. The grad will sit outside, you are right. Let me erase it. This is approximately equal to grad with respect to phi, right? This is what we have been doing. For theta also we did the same thing, right? And this is the exact case where the grad will not go inside the summation. This is the case where grad will not go inside the summation, but it is Gaussian. The distribution z is coming from Gaussian. And we know that there is another way of sampling Gaussian, where you sample Gaussian from the standard Gaussian and then do a scaling and shifting of that. So you do mu plus sigma times z and then use that to give mu plus sigma times, not z, this z is something else, so let's say epsilon. And then use that, that will give you your z, and then use that to write this thing, right? You can also do that. So the alternative way of doing this is, so I'll use different color for this thing, let's say, so that these are alternatives, right? So this is alternatively, this is equal to gradient with respect to phi 1 by k summation over j b mu plus sigma epsilon j, where your epsilon j is coming from, it is being sampled from standard normal, standard Gaussian 0, 1. That is the, I mean, I'm sure all of you know about that, that mu plus sigma times standard Gaussian gives you the Gaussian distribution of, right? So this is coming from Gaussian 0, 1. Please check the two expressions and see if that is making sense or not. I mean, it is very simple, should make sense, but yeah, it should make sense. There is nothing difficult here. This is a standard transformation of Gaussian distribution, right? And this is a deterministic transformation, by the way. I mean, if you have a sample, this is a deterministic transformation. Mu and sigma are not random, right? Okay, fine, no question. Hmm. No, no, epsilon is not connected with theta or phi. Hmm. No, will it change? Sampling from standard normal. Mu and sigma will change, which is deterministic. Epsilon will still be from standard Gaussian. Epsilon is a standard Gaussian. Mu and sigma will change, and as a result, the term inside will now be from a different distribution. But epsilon distribution is same. It does not change. Epsilon is from standard Gaussian with fixed parameter. I mean, standard Gaussian by definition is fixed parameter 0 and 1, right? So now in the left hand side, the purple one or the violet one, uh, the issue was that the samples were coming as a function of phi, so we could not push that gradient inside. In the right hand one, that issue is now not there. It's not coming from some distribution which is function of phi. It's coming from a distribution where the parameters are constant. And obviously, those parameters are inside, so but that's a deterministic mapping, so you can take the derivative gradient of that. So in this case, you can push the gradient inside. And if you push the gradient inside, what do you get? So this is equal to 1 by k summation gradient with respect to phi b mu plus sigma epsilon k, right? Okay. This is your reparameterization trick. In simple words, transform your distribution or transform your samples using a deterministic mapping so that you do not sample from the distribution the parameters of which you want to update, or the parameters of which with respect to which you want to take gradient, something like that, right? The basic trick is that you don't draw samples from a distribution the parameter of which are supposed to be updated. You draw samples from a distribution where the parameters are fixed so that the gradient can go inside. Now, what are the limitations of this reparameterization trick? One, I already told you that it is only applicable for continuous. The other one is that you need a deterministic mapping such as mu plus sigma times epsilon. If that deterministic analytical mapping does not exist, then you cannot use this reparameterization trick. So this reparameterization trick you can only use if there exists a deterministic mapping uh, such as the one that exists for Gaussian. Okay, so that is the basic bottleneck or drawback of this. Yes, that you decide. You think about that. Okay, you think about that. Why not? Okay, okay. And if you are not able to find the answer, I'll tell you later. But think about it. Hmm. Sampling. Correct. Exactly. We are basically reparameterization. That's why it's called reparameterization. Not necessarily. There are some other distributions where this kind of deterministic mapping exists. So as long as you are able to sample from a fixed distribution and then perform a deterministic mapping or transformation of that sample so that it comes from the target distribution, you can use this. But that deterministic mapping need not exist. For example, assume that you are sampling from uniform. Now, for going from uniform to Gaussian, you know it is inverse CDF you have to do. Inverse CDF is not deterministic. You cannot use this trick with inverse CDF of the Gaussian, let's say. Gaussian inverse CDF need not be deterministic. And if it is not deterministic, I mean, deterministic means it is deterministic but not analytically solvable, I mean. So it is still deterministic but not analytically tractable. So if it is not analytically tractable, then you are stuck. So the trick is simple. There is a huge possibility. Okay. Parameters are always well defined. If that form is analytical, the gradient of which exists, let's put it that way also, then you can. With discrete, the gradient will not exist. It is zero at some places, right? So that will go. Hmm? I just answered him. Asking. I just answered him. You missed it when you're asking. Because it's discrete, right? The gradients are not defined at many of the points. Obvious, right? That one. Reinforce, I have to check. I have not checked reinforce. That is generalized, but I do have to check whether that applies for discrete or not. I don't know. The reinforce one. Okay, that I need to study. I have not never used the reinforce one. Okay, coming back. Any question? This okay, right? So this is how you compute gradient in VAE. With respect to theta, it's straightforward. With respect to phi, you use this kind of trick to compute the gradient. Okay. But gradient computation was only, I don't know, 50% of the problem, let's put it that way. The other 50% of the problem, which is probably a bigger problem, so maybe not 50%, maybe more. The main problem is that the number of parameters in this case, whatever we have discussed till now, is function of the number of data you have. So naturally, this will not be applicable for problems where you have large amount of data, because phi, the number of phi is function of the number of data points you have. So if you have a billion or trillion data set, it will have trillion times some parameters. So this is naturally not scalable, and that is purely because of this fees. This phi I to 1 to m we were seeing, because of this fees, that is the problem. Okay. So we need to solve that problem, and if that problem is solved, then we are kind of good. Not really. You are taking with respect to theta. And what is this L? What is this L? This one, right? P of x comma z, you know actually. No. What is P of z? Gaussian. That's why I recapped the first whole thing. P of z is Gaussian. P of x given z is Gaussian. You multiply the two, P of x comma z is, what you don't know is P of x, because you cannot integrate out theta, z. So P of x given theta is intractable, P of x is intractable, P of z given x is intractable. P of x comma z is not intractable. P of x given z is not intractable. P of z is obviously prior, not intractable. So that is why I recapped it, because you should always keep in mind this q and or whatever we are bringing is only variational parameters or importance sampling, optimal importance sampling density. Our original thing is still P of z, from which we want to sample, and those samples we are want to use for probability of x given z. So that has not changed. It's just q came into picture because of the what you were saying, that Monte Carlo, the crude Monte Carlo was having a very slow convergence, so q came into picture. And then q optimum one was P of z given x, that was intractable. So this fees came into picture. So all of this came into picture because we want to accelerate and solve it. P of z is still there. It is not appearing, but it is still there. And your model is still that you will sample from z and then propagate through P of x given z. So That's why I did the whole recap, because this is a very common confusion, specifically when there is a 1 week gap. So that means 1.5 week from when we did that. So it easily, because there are so many things coming, it is very easy to get distracted, right? Okay. So yeah. So this, now with this setup, you can compute the gradients and use it. However, what I was saying is that, however, major challenge remains, and that major challenge we have already talked about. This one is number of phi is equal to number of data point. It's not that it is not, I mean, it is obviously because of this it is not scalable, but you can imagine if I get a new x, right? New x, and someone asks me what is the likelihood of that data, of that new x. I do not know phi for that new x. So even for evaluating likelihood during inference, I will first need to solve an optimization to find out what is that phi for that new x. So even that is problematic, right? So you can imagine that this is not only problematic in generating samples or learning, it is even more problematic when you are trying to evaluate, let's say, the likelihood or the probability or anomaly detection, let's say, as an use case, right? So that's a genuine problem. What is the solution? The solution is to amortize it. So to amortize, so what is the solution? So as a solution, we amortize it. Amortizing it in this case means, in all cases means actually, that we will introduce a new network will introduce, which will take x as input and will give me the phis, the variational parameters. So instead of learning the phis, we bring another network into picture that will give me phi as a function of x. And so my job will now be to learn the parameters of this network. Let me write it down and then I will say why is it useful. So as a solution, we amortize it by introducing let's call it f lambda of x, or f lambda, to be very honest, okay, where f is a neural network parameterized by lambda. So this means that z, this not z actually, phi I should write. So phi is now equal to f lambda of x. What we have done here is very simple. We are now saying, remember that phi was variational parameter. These variational parameters were function of data point. So if they are function of data point, why should we learn it for each data point? Why can't we have a mapping that takes the data point and give me those parameters? Right? Is this the best way of doing it? Yes and no. Yes, because it will make it scalable. No, because that process is still more optimal than this one. If you optimize it properly, that will probably give you better results. But that's not scalable, so you cannot use it for large data. It will be optimized because we will optimize for lambda, but global sense it is never optimized, but it is more approximate, let's put it that way. It is a neural network, right? So everything is a surrogate, but because neural network is a universal approximator, and because phi is a function of x, in theory I can argue that this will be able to learn the exact phi because I am optimizing for it, right? So I can always argue for that. In practice, I will not be able to learn because you will get to realize that in a short while, because I will do something more. That is why I will not be able to learn. Previously, remember, we were optimizing phi and theta separately. Here I will optimize them together, because again, that is another step which is expensive. Anyways, so what I am doing is very simple. Remember that I need phi, my variational parameters. But the problem is that the number of variational parameter increases with the data set. It's a function of data set. The number of data point is equal to number of phis, right? But we also know that these variational parameters are function of x. If we know that, why should we not introduce a network that will take the data point as an input and give me the variational parameters? Once I know the variational parameters, let's say that is Gaussian, let's assume that, so I can sample from that with these parameters. And once I sample from that, I get my z. Those z will now go into my decoder, the second part of the network, and that will give me samples of x. I will draw it, but those decoder encoder will come later. But is this making sense or not? What we are doing? I'll repeat once more. So remember that our objective was to find out the variational parameters. But the variational parameters were increasing as the data points were increasing. And the variational parameters were function of the data itself. So then we say that we introduce a network, a nonlinear function basically, that will map from the data to the variational parameter. And this network is parameterized by some new parameter lambda, which are unknown, which we need to learn. Okay? Any question? No, that will come later. For now, I just do this, nothing else. Clear? Okay. So if this is clear, so then this network is now going to give me my P, right? And if I have to draw, it will look something like this. So I'm not drawing it exactly, but let's try. So I have my x. So there will be some network. Let's call it f lambda. F lambda. This network will take x and will give me phi. And phi is a vector. It will phi1, phi2. You can decide what that dimension is now. Okay. It is not function of your data point. You can decide how many phis you have. No, it will not be. It will not be. It will not be. So once you have your phi, you can use those phi and sample z, because those phis are your variational parameters. Take the variational distribution q of phi and sample from there. Well, maybe I should write it like this. So phi will go into your q, which is the variational distribution. And the distribution family you have selected. That is the whole idea of variational inference. You select the distribution and try to tune the parameters. It will go into q, and you can now sample from it. So if you sample from it, you will get z. Z will go into another network, which is parameterized by theta exactly. Let's call it what? Maybe write f theta. This will give you mu theta and sigma theta, right? You take these two things. Now you already know probability of x given z, put it there, and that will give you your x generated. Clear how the network is now looking? Now it is the VAE that you are aware of, right? You give x, you recover x. That's why the name autoencoder is there. You call it autoencoder because anything is autoencoder if what you are giving as input is what you are getting as output. That's the autoencoder. So, so you can see that I'm giving x and getting x tilde, which is like some reconstructed version of that. So that is why you call it autoencoder. You call it variational because obviously there is z and we are using variational inference and all of those things. So that's why we call it variational. And the whole thing is we call variational autoencoder. Slightly different because your loss will never be. It is during training it will be same. Training during test using inference you don't need the first part. You will just sample z from and we'll see how where we'll sample from. During we'll come there. Wait, we'll see how can we sample this, right? I mean, without telling any more details, you know that z will be sampled from P of z, which is Gaussian 0 and 1. So z will ultimately be sampled from 0 and 1. How we are coming there? Okay, we're coming there. Okay, so this is your autoencoder structure, which generally in books or in many places look something like this. Uh, so we look something like this, and then this generally keeps on reducing. That's why you call it encoder, and then it starts increasing again. This is how an autoencoder looks generally, and obviously you can imagine that this will be connected. So I am not going to draw everything, but you can imagine. This is the autoencoder diagram. This is your x. This is your latent. So sometime you write it H in autoencoder. In VA you write it as Z, and then the output is this is your x tilde. Okay. So what we did, we started with latent variable model. But in latent variable model, we realized that we cannot train the model. We cannot train the model because z is unobserved, so we cannot compute probability of x given theta because I need to integrate out z, and that I cannot do analytically. I can do it by sampling, but that has very slow convergence. So we said, okay, then let's do importance sampling, which has increased convergence. But to do importance sampling, we need the importance sampling density. We found the importance sampling density. It was P of z given x, which also is interactable. So we said, okay, let us introduce variational distribution and variational inference. We did variational, came up with phi, but now the phi was function of number of data points, which is not scalable. So we said, okay, now let us, because we know that p's are function of x, let us introduce another network there, which is f of lambda. And this f of lambda now is making it scalable, and that's our variational autoencoder. Any question? No, it will come there. That will come there. That is supposed to come. I have not yet gone. There's still some time remaining for me to wrap it up. Correct. But you are forgetting that I need to train the model, and for that I need to compute probability of x given theta. Right? That's the likelihood, which is equal to probability of x comma z given theta, integration over dz. And to do that, we have our variation, we have our importance sampling density, right? So that integral to compute that training time, right? To compute that, we have our importance sampling density, which is actually intractable. So we have our variational distribution for computing that integral during training. That integral during training cannot be computed without bringing Q into picture. And the best Q is, I mean, because it's variational, is the no. Q means not in this diagram. In this diagram, you will find you get variational parameter and those variational parameter you get for a distribution you have assumed. So Q is the variational distribution, parameterized by the variational parameter phi. Right? Remember, Q you have assumed, because in variational the whole idea is I have a distribution which is intractable. Let us assume a tractable distribution and then try to match the tune the parameters so that this tractable distribution is as close as possible to the intractable. Because in real world you need to compute the expectation with respect to this intractable distribution, which is probability of z given x. But that you cannot do. So we are approximating the likelihood actually by doing it with respect to q of z, or q of phi actually, q phi of z. And to do that we need phi. Right? By you will need, wait, we need it. We definitely need it. Okay, but the form slightly changes and I'm coming to that. Any doubt? Correct. The variational name comes from variational inference. Variational inference is a class of machine learning algorithm, Bayesian inference mostly, where you, if there is an intractable distribution, you assume an approximate distribution known as the variational distribution, and you vary the parameters of the distribution, vary, so that this variational distribution is as close as possible to the original intractable distribution. That's what variational distribution is. Okay. Inference or predict? Okay, that's a very good question. Okay. So inference, actually there is a meaning, and then in machine learning there is, the meaning has changed actually. So in machine learning generally inference people means prediction, right? But in Bayesian statistics inference is not prediction. In Bayesian statistics inference means you are inferring something. So generally training is actually inference in Bayesian inference, because you are inferring the unknown parameters, the weights given data. So inference in Bayesian statistics is actually training, which is inferring the unknown parameters from data. But in machine learning, we call it training, and prediction we call inference. And so there, terminologically, there is some conflict there. Strictly speaking, UK English probably inference means, because UK is where English started, right? So inference means training, inferring the weights given data. Correct. Correct. Yes, but in reality, those factors will not be known to you. So you are assuming that there are some factors that are resulting in the data, but those factors you do not know. And those factors might be some abstract factor which human cannot make sense out of also. Not necessarily, right? Let's say I want to generate MNIST. MNIST is a data set, right? 0 to 9 handwritten data set. Now, you can imagine that the factors are 0, 1 to 9, and that's fine. But when you actually use it with 10 factors, it does not work. You use 100 factors. And when you use 100 factors, you do not know what those factors mean. Right? So, you are right. Ideally, we will want those factors to be interpretable, but most of the time they are not. So they are kind of abstract which human cannot make sense out of. But again, at the same time, there is a line of work I mentioned earlier, also the Koopman work, right? Where people are trying to train, let's say, variational encoder or coming up with the generative model where the Z's also have meaning, some meaning to make it interpretable, right? But not necessarily will always achieve that. The vanilla one does not, definitely Z do not have any meaning. It's mostly noise. Gaussian 0, 1 is noise, right? But yeah, how sensitive they are is a important question. You can keep other samples same, keep on changing one sample and see how does it influence, right? For example, when I take 100 ones, right, 100 Z's for MNIST, it is possible, right, that if you change one of the Z's, maybe the digit is becoming thicker and thinner, depending on what value you are taking. Even that can be a feature. The circle, for one of the factor, it might rotate. For one of the might, it might translate. So you do not know what those factors actually are, But yes, you do want to make sense out of it. Whether we will be able to or not is a very problem dependent scenario and is an open problem at the same time. Right? Okay. So any question? So, clear until now? So if this is clear, one more thing we will do, which is to revisit the loss function. Okay. So by the way, VAE is a amortized latent variable model. I mean, that's all we did at the end, right? With this setup, this diagram I'm not completing, but yeah, maybe let me draw one more. This does not look good actually, so let's draw one more. Okay, and then the other part you can draw. Okay, loss function. Let us go back to the loss function and see if we can make some sense out of the loss function. What is LO actually doing? Is it doing something meaningful, or is it just an mathematical quantity, a mathematical lower bound that we try to maximize? LO by definition is a mathematical lower bound, but can we make some sense out of it, or can we rearrange it to make some sense out of it? Let us try to see. Okay. So revisiting LO. Okay. So how did LO look like? LO, okay, by the way, I have not written the algorithm, I'll write it, but first let us revisit LO, then I'll write it. So L, lower bound, is now function of what? X, then Z to is always, I'm not writing Z. X, theta, and lambda, not phi. Mainly lambda is what I was asking. But yeah. So X, theta, lambda. This is what it is a function of, right? And how will it look? How will it look? Integration of Q lambda. Hmm? Correct. And those phis are now function of the neural network, which is parameterized by lambda. So it's now a function of lambda. Q was Q function of lambda. Theta is function of lambda, and Q is function of theta. So Q is function of lambda. Right? Q lambda of Z. Right? Because it was previously Q theta of Z. Those thetas are function of lambda, so Q lambda of Z, which obviously we'll get using a neural network. And then log P of x comma z given theta, right? X comma z given theta, which is actually equal to P of z multiplied by P of x given z comma theta. Keep that in mind. Why is it disturbing? And then here also you have Q of lambda z dz. This is my elbow. Everyone agrees? So let us do some operation on that. Okay. So first operation we will do is the log a by b, log a minus log b. So this is equal to integration Q lambda of z log of P x comma z given theta. So we will write it as P of z, P of x given z comma theta, or P theta of x given z, right? Minus, tell me, minus log of q lambda z, right? Dz. See what we have done. Log of a by b is equal to log a minus log b. Log a is actually equal to x comma z. So that I have decomposed into this form. And this form we know from the first lecture on latent variable model, right? Clear? Now I will do a small trick. I'll introduce a log of Pz into the system. Log of Pz is my prior, the z that is Gaussian, by the way. So let us introduce that. So this is equal to integration q lambda of z log of Pz p x given z comma theta minus log of Pz plus log of Pz. I can always do that, right? Minus plus will cancel out. And then minus log of q lambda of z dz. Okay? Simple. The first two term I will combine. The second two term I will combine. So what happens when I combine the first two terms? Log a minus log b is equal to log of a by b, and then it cancels out pz and pz. So I will end up with only the x given z, right? So let us write that. So this is equal to, the first term is q lambda, what is happening? I am not sure why it is sleeping today. Q lambda of z, and then log of p of z, p of x given z comma theta divided by p of z, and this cancels out dz. This is my first term. The first term after combining all of this thing, this is what I get. Okay. Let's move on to the second term. And you can see I have separated out the integration now, dz I have written. So the second one will be a different integral. The second term, what is it? You should be able to tell. It is what? It is some known quantity. Look into it, the second term carefully. The second term is KL divergence, negative of KL divergence between Q of lambda z and P of z. The second term is actually KL divergence, right? And I will write a negative sign. Integration so Q lambda of z will stay outside, and then log of, because the negative sign is outside, so Q lambda of z divided by P of z dz. It's the KL divergence, right? So with that, first write the first term. The first term is expectation with respect to q lambda log of p theta. Now theta I am writing in the subscript. I will again repeat, it's the same thing, right? First term is this one, expectation with respect to q lambda, and then whatever is inside, and whatever is inside is known to you, it is Gaussian. P of x given z is Gaussian, so that is Gaussian, right? And you are maximizing the log of Gaussian. You can imagine you will get a mean square loss there. If I do the calculation, I will end up with a mean square loss in that one. Minus KL divergence between Q lambda of z and P of z. where P of Z is Gaussian with 0 and I. So basically this is what you are doing. When you train the VAE, this is what you actually train for. And now see what is the first term. It is known as the reconstruction loss. If you put the, remember that P of x given Z is Gaussian. To put it to be Gaussian, log of Gaussian, it will cancel out. Exponential there is, because log and exponential, it will cancel out. And in the exponential, in the top, what is there? Square. So you will get a mean square loss there. Okay. So, and we call it reconstruction loss because it is trying to match what x you gave and what x you are getting. It is trying to match x and x hat. Right? The second one is scale divergence. It is trying that whatever this encoder part q lambda is predicting or f lambda is predicting, that should be as close to Gaussian, standard Gaussian as possible. This is a scale divergence or regularization. Now you see a negative sign in between. Why is there a negative sign? Because you are maximizing it. So negative of scale divergence you always minimize. So negative of scale divergence you will always maximize. And the first term you anyways maximizing. In practice, when you put a negative sign in front of the first one, make the second one as positive and optimize that. So because most of the optimizers are minimizers. So you will get here if you do, you will get negative of mean square error. Because exponential of minus half x minus mu by sigma square. So there, because of that minus sign, you will get a negative of that. So negative mean square you will maximize. But what is x hat? I will do that. But what is x hat? Prediction from what? What is the input? Z. So this is function of only theta, right? So that prediction when you put is x minus mu, right? And that mu is coming from as a function of z through the neural network, right? And then sigma square is sitting in the denominator, assuming univariate, otherwise inverse, and that is also coming from the neural network. P of z. Louder. Again, what is q lambda of z originally? P of z given x. P, forget about lambda. Q of z, which is the variational distribution. The optimal one is P of z given x is not guaranteed to be Gaussian, first of all. You have assumed it to be Gaussian, that's why Q came into picture. And now you are basically saying that the encoder part, you give me parameters that will make the mean and standard deviation 0 and 1. That's what it's doing. That's exactly what it is doing. It is saying that give me the weights such that p's become 0, 1. Not repeat again. Q phi is not intractable. P of z given x is intractable. That is the optimal one, and you cannot compute it because P of z given x is equal to P of x comma z divided by P of x. And P of x is intractable. P of z given x is intractable because P of x is intractable. P of x is intractable because you cannot integrate out z analytically. Because z is high dimensional. So P of z given x is intractable, but it's at the end of the day a distribution over z. So assume qz to be that distribution and find out the p's. But ultimately, with all of this, we are saying, we are coming to a conclusion that those fees I want to find out should be as close as possible to standard Gaussian. Now, the important portion here is that it should be close to 0 and 1 independent of what data you are providing. So, you have to find parameters that can take any x and take it to 0 and 1. So, it is not always 0 and 1, it is P of z given x, and you want parameters that will take it as close as possible to 0 and 1. Mu and sigma for what? No, we are not saying that. We are saying we are optimizing for that, but that is not the best one, because we have, by introducing Q, you have ensured you are not doing the original one. Is the second term exact? Is the second term exact? If the second term was exact, what should be the expression? Let's start with that. Assume I could do everything exactly. What should the second term look like? No. KL divergence between what? It should be between P of z given x and P of z. We could not do that. So no matter what Q we are doing is an approximation. We could not write it in terms of P of z given x, right? So then means it is not optimal. It's an approximate likelihood, which is the biggest limitation of VAE, that you cannot evaluate the exact likelihood. That is the whole point of this VAE limitation, which will be sorted in the flow based that we'll go do next, hopefully. Okay. Any question? I'm only answering question from this group. Others might also question. Yes. So for the anomaly detection, you will use the encoder part also will be needed for anomaly detection, because any new data you get, right, anomaly, you want to see whether it is coming from the same distribution or not. So what will you do? You'll put it into the X and get evaluated and somehow try to calculate the likelihood. You will not be able to calculate the exact likelihood, that's okay, but you will be able to calculate, I mean, you will be able to calculate in some sense. So that likelihood you will calculate, and then from that you will take a decision that whether it is high probability or low probability that it belongs to the distribution you have learned. Elbow also now, you can calculate the likelihood also now, because Z now you have samples, because you have learned lambda. So that means Z now is not unobservable, or Z you have observed. So you can sample Z as many times as you want. Correct. It is an approximate, no doubt, but you can calculate that approximate one. That's what I'm saying. It's not exact, but you can at least calculate that. Neural network is never exact. Even if it was not approximate, it's a non-convex optimization. But you can evaluate it, yes. Right? And yes, and that is important. How do you sample from VAE? Any idea? I want to sample from VAE. What will I do? The model is trained. So lambda I know, theta I know. How? So correct. So only the second half is needed. We'll start from the middle, and only the second half I will use for sampling, right? Everyone follows? If I have to sample, it's only the second part that I care about, which is I will sample Z from Gaussian and then propagate it through the rest of the, which is called decoder, and that will give me my samples. So for sampling, the encoder part is not needed. The encoder part is to assist you with training when it comes to sampling. But that is not entirely true. For anomaly detection, the encoder part is needed. Correct. Correct. One. Correct. Yes. That is another way. Yes, that is another way of doing it. Exactly. Right. Correct. Then just do the decoder part. So again, encoder decoder I'm using, but let me draw it here. What is encoder? What is decoder? I mean, it is already drawn, but mark it. So this portion is known as encoder. because this is encoding it, right? I'm using these terminologies, but yeah, this portion is known as decoder. Because the first portion is kind of encoding it into some variable, and the second portion is decoding it. Okay, so that's why it's encoder decoder kind of structures, hence autoencoder. Variational, hence variational autoencoder. Lastly, the training algorithm. You can write it, but it's very simple. Let me write it down. That I was supposed to write earlier, but I forgot. But I think this you can now tell me. Training. So what is step 1? Initialize what? Theta and lambda. I can write theta 0 and lambda 0, that's fine. Step 2, select xi. I mean, you can select a batch also, but I'm doing it one at a time. So SGD I'm doing, but it can be batch. You can use Adam and all of those things. Step 3, compute 2 gradients and step 4, update theta and lambda. Step 5, go to step 2. So this is how we will train, right? And you can see that we are training it now together. That is another reason it is less accurate. So, but it's at least it works, or it can at least handle large data set, right? So there is always a trade-off. There is nothing perfect that doesn't exist. Okay, so it's always a trade-off. Any question? Otherwise, we are done with latent variable model. Next lecture, I'm thinking of starting flow-based model, which I will finish in 1.5 kind of lecture. Half. Okay. Not flow matching, flow-based model. Normalizing flow. Hmm. Yeah, well. You know, P of z is Gaussian, right? It's a latent variable. We started with the first. It's a standard normal. You are forgetting. What is z? Right? Because all the variational came in between, I understand it's very common. Until you do it yourself, read it, it's very usual to forget. And that is why I had 5 slides of recap. Mhm. Q of lambda z is Q you assume, right? And one of the assumption is obviously you can assume Q to be Gaussian. Uh, lambda is the parameter of the neural network that you train for. Q is the assumed family, so let's say Gaussian, and lambda you train for and find out. But Q need not be Gaussian. You can assume Q to be something else also, but it's on you. Generally, in variational, the obvious choice is to assume it Gaussian, because then you can do things in a tractable manner. Okay. Z given X we never choose. X given Z we did not choose to be Gaussian because of this reason. X given Z we choose to be Gaussian because X given Z will come only in the first term, right? And that we chose Gaussian because it will be simpler, because the example, remember, once you have male versus female, the male pictures will be like similar, so it will be some similar. Once you condition on the factors, the distributions are simpler. So that's why you choose it to be Gaussian, but I also told that you need not choose it to be Gaussian. You can choose it to be an autoregressive model. You can choose it to be a mixture of Gaussian. No one is stopping you from doing that. Gaussian is just an assumption we make, and that assumption results in the first term to be mean square. If we make it something else, the first term will not be mean square. Second term has nothing to do with that. I mean, the calculation has everything to do with that, but the term as such has nothing to do with that. Okay? Because it is not doing much about x, right? It is regularizing your not okay. When you say regularizer, that regularizes something. In most of the time, regularizer regularizes your weights and biases. In this case, that is not happening. It is regularizing your latent variable. It is forcing your latent variable to be Gaussian. So that's a regularization, right? So that's why we are calling it regularizer. Okay. Any other question? I thought I'll end the lecture today early, but already 5 minutes past 7:20. Okay. Thank you.